Well, hello and welcome. This is Mr. Roberts at Shasta High, and we're going to go through the study team test for Chapter 4. Let's start with question 1. It says, simplify each expression, remove all common factors, i.e. giant ones, and don't leave any negative exponents behind. A couple other things we talk about in class as well. But let's take a look at this first one. I can see, first of all, it's just multiplication. There's no terms here. This is just a giant monomial. And I'm going to focus just arbitrarily on this chunk first. And I see this thing is getting squared, so I'm going to go ahead and square that. If I square that part, well, let's just write this part down first, right? This is just 5b to the second power. But if I square this other thing, that means it's 3b to the 6th times another 3b to the 6th, which looks like 9 times b to the 6 factors, 12 factors of b, and then times b to the negative 10th. If I take this another step, I can see that I've got a 5 and a 9 that I can multiply. Those are numbers, they're not exponents. 5 times 9 is 45. And then I have more factors of b, right? This is b to the 2nd times b to the 12th is b to the 22nd. And then when I multiply that by b to the negative 10th, it's just going to be plain old b to the 4th. What? B to the 12th times b to the 2nd is, I'm sorry, did I say 20? B to the 2nd times b to the 12th is b to the 14th. There are 14 factors of b so far there. Then I multiply that by b to the negative 10th. Now, I can think about this one of two ways, right? I know b to the 14th times b to the negative 10th is just b to the 4th power. So my answer is 45b to the 4th power. But I could write this if I wanted to. This is b to the 14th times, or over, rather, b to the 10th. And I can see the exact same thing's going to happen here, right? If I've got b to the 14th in the top and b to the 10th in the denominator, that's still going to simplify to b to the 4th power. Moving on to part B. I have 15 over 5. 15 divided by 5 is 3. If I want, I could write this as 3 times 5 over, there's a 5, times an x to the 2nd. And this is a giant 1, so it's gone. In my denominator, I have this x to the negative 8th. And I know that that's equivalent to having x to the positive 8th in my numerator. So I end up with 3 times b to the 10th power for part B. 3 times x to the 10th power for part B. Part C, well, C looks ridiculously a lot like part B, doesn't it? 6 over 2, right, is going to be 3. So there's a 3 in the numerator. I've got an x to the 3rd. I've got an x to the 4th. In my denominator, there is this x to the negative 3, which is, it does not form a giant 1 with the x to the 3rd in the top, right? Those 3 factors of x, this is equivalent to me writing this as just an x to the 3rd power up in the numerator. So 1 over x to the negative 3rd is x to the 3rd in the numerator. So across the numerator, what do I have? I have a 3, and then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 factors of x. So 3 times x raised to the 10th power. And then our last problem is all numerical, and of course we could use we could use a calculator to evaluate this, but I'm not going to. 8 divided by 4 is 2. So I'm going to just write this as 4 to the negative 2nd over a 2. And then this is just 2 over 1, right? 8 over 4 is 2 over 1. Well, this is multiplication. So these two, right, do form a giant 1. 2 over 2. What am I left with? I'm left with 4 to the negative 2nd power. And 4 to the negative 2nd power is the same as 1 over 4 to the positive 2nd power, which is the same as 1 over the number 16. So 1/16 is the answer for part C. Let's jump down to these equations that we're asked to solve. The first one is an excellent example for the technique we call fraction busters. I can see that I have factors of 2, a 3, and a 2. So all I need is to push a factor of 6 across all of these. So the idea here is that if I multiply each one of these terms, and there's several terms, right? This term, this term, this term, and this term by the number 6, then all of the fractions will go away. One thing I like to do when I do see that some of my terms have a binomial in the numerator, I will place parentheses there to remind me that whatever I'm left with in the top has to be multiplied by both the 4x and the negative 1. So I'm just going to go ahead and write this out visually. This is so that we can see all the steps. This is 6 times a 3x over 2 plus 6 times the quantity of 4x minus 1 over 3 minus 6 times 4 equals 6 times 5x all over 2. So when I take a look at these, there's lots of simplification that can happen. The first thing we'll point out is that there is a 6 divided by 2 is 3, so this becomes 3 times 3x, which means this is going to be 9x. 6 divided by 3 is 2, so I'm going to be multiplying both the 4x and the negative 1 by 2, which means this will become 8x minus 2. The next thing that we're going to have here is 6 times 4. This is going to be a negative 24. And then finally on the other side, 6 divided by 2 is 3. So this is going to be a 3 times 5x, which is 15x. So no fractions. These two together are going to make 17x. If I combine negative 2 and negative 24, there's a negative 26. And on the other side, there's a 15x. I'll just take away, let's see, we can go either way with this. I'm going to go ahead and subtract 15x from each side. When I take away 15x from the right-hand side, I'm left with just a 0. Over on the left-hand side, when I take away 15x, this becomes a 2x, and then minus 26. If I add 26 to each side, I get 2x is positive 26, and then therefore x is the number 13. So x is 13 is our answer for this first one. Highly recommended, especially considering how much time you have, that you take that value, store x is 13 into your calculator, and plug it into both sides to just kind of make sure that it does make indeed the left and the right-hand side the same number. Let's move on to part B. Part B, this is an exponential equation, right? We've got our variables up in the exponent, and our solving technique is to rewrite it so that the bases are the same. I see this base of 2 here, and I might play with factors of 2. Like, for example, I know 2 to the 0 power is 1, 2 to the first is 2, 2 to the second is 4, so these are 2 to the third is 8. And that's interesting because there is an 8 here. If I go the other way, right, I can look at 2 to the negative first. Oops. 2 to the negative first is 1/2. 2 to the negative second is 1/4. And 2 to the negative third is 1/8. And that's what I've got here. So what I'm going to do is choose to rewrite 1/8. I'm going to rewrite that as 2 to the negative third power. So I'll just rewrite the left-hand side. It's going to be 2 to the 3x minus 9 power, and that will equal 1/8. Nope. I'm going to rewrite that as 2 to the negative third, and then I'm raising that to the x minus 5 power. So what I have here is a power raised to a power, right? I've got 2 to the negative third, and I'm raising that to the x minus 5 power. So when I raise that power to a power, that side's going to become 2 raised to the negative 3x and then plus 15 power. So I distributed that negative 3 to both the x and the negative 5. On the other side, it's still 2 to the 3x minus 9. Now that my bases are exactly the same, right, these bases are both the number 2, right, I can just set my exponents equal. The only way these are ever truly going to be equal is if 3x minus 9, right, the exponent on the left, is the same as negative 3x plus 15. If I add 3x to both sides, this is 6 times x minus 9 is 15. If we add 9 to each side, we've got 6x is 15 plus 9 is like 20, what is it, 24? Yeah, this is 24. And then we're going to divide both sides by 6, so x is 24/6, which is the same as 4. So x is the number 4. Again, if time permits, right, plugging that in and making sure that both the left and the right-hand side are the same number is a great confirmation that your answer is correct. Let's go down to part C. On C, we've been looking at this thing called looking inside, and clearly this thing inside of the square root has to be some number, right? But before we can really figure out exactly what that is, just thinking about it, it's probably best to isolate the square root portion of this. So there's two things I'm going to do. I'm going to begin by undoing this adding 12 by subtracting 12 from both sides. And then I'm going to undo multiplying by 7 by dividing both sides by 7. So it'll look like this. This is going to become 7 times the square root of 4x minus 3. And that will equal 61 minus 12. You know what, I'm just going to write that 61 minus the number 12. This is me not doing arithmetic. And now I'm going to divide both sides by 7. So that means the square root of 4x minus 3 has to be the same as 61 minus 12 divided by 7. There, I'm not doing arithmetic. I should do that arithmetic. I think that numerator is 49. 49. Let me check with my calculator. Yes. And the denominator is 7. So this is actually the number 49 divided by 7 is the number 7. Okay, so the square root of something, right, the square root of some value equals 7. That means that this thing inside, right, if I'm taking the square root of this number and getting an answer of 7, that means that thing inside has to be 49, right? So there's a lot of ways to think about that, but I know a lot of my square facts, so 4x minus 3 must be the number 49. 4x minus 3 must be 49. Why does it have to be 49? Because when I take the square root of 49, I will get 7. So that's the thinking. Add 3 to both sides, 49, 50, 51, 52. So we've got that 4x must equal 52. And then if I divide both sides by 4, x has to be 52 divided by 4, which means that x has to be the number 13. So x is 13. Again, plugging that value into this original equation and getting confirmation that it indeed makes both sides 61 is definitely worth the effort and time. Last question in this section says, solve this thing. And we have, I don't need a keyboard. We do have this binomial, it's not a binomial expansion, don't say that. You're just multiplying two binomials here. So if I multiply these binomials, you could use an area model to organize your work. But I do know that it's going to have these 4 parts, right? It's going to be a 3x times an x, so it will have a 3x squared. And then it'll also have a 3x times a 5, which would be plus 15x. And now, so what I just did was I multiplied this 3x times both the x and the 3x times the 5. Now I'm going to multiply this negative 2 times both the x and the 5. And I will get all 4 of the things that a generic area model would have. So now I've got negative 2x and then minus the number 10. So if I combine those, actually, there's a minus 10 right there, right? So then let's write the rest. So there is a 12x and there's another negative 10 that I should not neglect to write down. So there's a 12x and another negative 10. And on the other side, there is a 3x squared plus 20. What's convenient is the fact that both of these have a 3x squared, so that's completely gone. I'm just subtracting it from both sides. If I collect my like terms on the left-hand side, I've got 15x and 12x, which is 27x. And then from that, I'm going to take away 2x. So I believe when I combine those like terms, I get exactly 25x. And then I've got a negative 10 and another negative 10, which makes a negative 20. And on the other side, it equals 20. If I add 20 to both sides, 25x is the number 40. And if I divide both sides by 40, I get that x is 40 divided by 25, which reduces to 8/5. So x is 8/5 is the answer for part D. All right, quickly on to page 2. It says multiply. You may want to use a generic area model to organize your work. Remember that squaring a polynomial means you are multiplying it by yourself. What a nice thing to say. I don't feel like that's necessary that I say it, but it's important to say because we're trying to avoid the common error that we see with this, right? What we will often see written down is 4x squared minus 9. It is definitely not that. When I'm doing this, I'm multiplying a 2x minus 3 times another 2x minus 3, right? To square something means you're multiplying it by itself. Now, I don't need an area model for this, but I haven't used one yet. So just as a review, if I wanted to, I've got a 2x and I'm adding then a minus 3 from that, and I've got another 2x and then a negative 3. So there are 4 parts that go into that product. This is 4x squared, and most of us would have gotten that. And also there's a negative 3 times negative 3, which is positive 9. The thing that we're missing, right, if we're not thinking about this carefully, is there's a minus 6 times x and another minus 6 times x. So this whole thing, right, has a product that is equal to 4x squared minus 12x and then plus 9. 4x squared minus 12x and plus 9 is the product of those two binomials, or it's what the result of squaring those binomials. On this one, I'll forego an area model and just be organized here. I have to multiply each term by each term. So I'm going to multiply the 5x times the 2x, and I'm going to multiply the 5x times the negative 5. And then also the 1 is going to be multiplied by both the 2x, and the 1 is going to be multiplied by the negative 5. So that will show me all 4 things that go into that product. 5x times 2x is 10x squared. And when I multiply 5x times negative 5x, I get negative 25x. And then 1, so that's the blue ones. Now the 1 times 2x gives me a plus 2x, and 1 times negative 5 gives me a minus 5. So when we collect up our like times terms here, we've got 10x squared minus 23x, 25 minus 2, and then minus 5. So this is the product of those binomials. And then the last one is the simplest form of this thing we call the distributive property. I'm going to multiply both of these, the negative 2x times an x and the negative 2x times a negative 4. And when I do that, I get negative 2x squared and then positive 8 times x. So that is the product of that monomial, negative 2x, times the binomial, x minus 4. All right, let's move on to question number 4. 4 has a graph. Ooh, okay. And we are asked to, don't need a keyboard, sorry, Klaus. We're asked to, first of all, graph the line 5x minus 7y equals 35. Well, that's in a nice format if I want to graph by finding the x-intercept and the y-intercept. But I'm going to choose to rewrite this in y equals form. So I'm going to subtract 5x from both sides. I will get 7y is equal to a negative 5x plus 35. So we can all see I just added, or I subtracted 5x from each side. And now I'm going to divide both sides by 7. On the left-hand side, we're going to be with just a y. And then I'm going to have negative 5/7 times x because that term got divided by 7. And then finally, 35 divided by 7 is going to give me the number 5. So plus 5. So again, what just happened there was every single term, this term, this term, this term, and this term were all divided by 7. Now I can see that my y-intercept is at positive 5, and I can also see my slope pattern is down 5 over 7. So if I was to graph this point, and then from here I would go down 5, 1, 2, 3, 4, 5, and then over 1, 2, 3, 6, 7, 7. I can clearly see where my x-intercept is, and I'll just repeat that one more time. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, and 7. All right, so I've got a nice idea of what this line looks like. Now, what am I asked to do? Well, I'm asked to graph that line. Okay, I've got it. Let me grab a ruler, line it up. And one thing is nice is if you don't have a ruler, like I always have index cards lying around, use an index card to draw a straight line. The line should extend, you know, all the way to the edge of the graph and beyond, and then there should be arrows indicating that it continues. So that is the graph of that line. Next, it says graph the line that goes through the point 1, -8 and is perpendicular to the line 5x plus 7y equals 35. Oh, it's perpendicular to the line we just graphed, right? We just graphed 5x plus 7y is 35. So we want a line that goes through the point x is 1, y is -8, right here. And it has to be making a right angle with this other line, the line we just drew. So look, if I'm going to be perpendicular to a line with this slope, the slope that I need is the opposite and reciprocal. So I'm going to be looking at positive 7/5. That means from here I'm just going to go up 1, 2, 3, 4, 5, 6, 7, then an over 5. 1, 2, 3, 4, and 5. Put a dot. Up again. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Now, it's beautiful, right? And I like it that it's kind of very convincing that I can see this. I'm going to rotate this ruler all the way around, actually probably 90 degrees from where it was. Line this up, and then go ahead and draw this line, extending it to both directions. Now, this line, right, it has a slope that is the opposite in sign and reciprocal of the one in red, and because of that, those two lines are perpendicular to each other. So that was part B. Part C says plot triangle ABC and plot triangle A prime B prime C prime given the following what? The coordinates of A, B, and C and the transformation. Oh my gosh, given the following. Okay, so this is worded terribly. Who wrote this? Probably me. So the points A are at -6. I'll use blue for this. So -6, -3. So -6, -3. This is the location of A. B is located at -7, -1. This is B. And C is at -2, +2. C. And we're asked to take this triangle and to rotate it 180 degrees clockwise around the origin. Okay, I got it. So 180 degrees is probably one of the nicest rotations because these points just become, I think they just become the opposites of what they were. I think they even stay in the same location. So C is going to go to, and I'll do this, I guess, yeah, C I'll keep in blue. C is going to go to the point, I made a little mistake there, didn't I? No, that was right. C is going to go to the point x is 2, y is -2. So before it was at -2, 2. Now they just took the opposite side. So this is C prime. So what's happened is this point, it's going to rotate 180 degrees around this point, the origin, and it's going to land there. Let's do the rest and see if we're convinced. A is at -6, -3, and I believe it's just going to go to 6, 3. So A prime should be at 6, 1, 2, 3. This is A prime. And then B prime should be at, B was at -7, -1, so this should be at +7, +1. This should be B prime. So I believe my triangles are, here's this one, I'm just sketching these. I'm not even using a straight edge, I'm sorry. And this one. And I don't, yeah, I'm convinced. And there is this rule, right? If you're doing 180 degrees rotation, XY gets mapped to the opposite of X and the opposite of Y. So if you're doing a 90-degree rotation, I know X and Y switch places, and then it depends on if you're going clockwise or counterclockwise. One of them changes sign, but let's leave that there. Question 5. It says, find the output generated by the given input. Okay, that's this part. So this function's receiving -5. I really want to see this written more often. 2 times a place for x, that's going to be squared, minus 5 times a place for x. The value of x is -5, and it's going to go here, and it's going to go here. I'm going to place a -5 here and a -5 here. When I square that -5, it becomes positive 25, and then I double that, that becomes positive 50. So this is 50. And I see mistakes where this is like the sign is wrong, plus or minus. Remember, there's the confusing thing is this. If you just type -5 squared in your calculator correctly assumes that you're just looking for the opposite of the number 5 squared, right? You're just taking 5 squared and then taking the opposite of it. That will always be negative. If you're trying to square -5, tell your calculator, look, here's -5. The negative and the 5 are all part of what I want to square. And when you square -5, right, -5 times -5 is positive 25. And then on the other part here, I've got -5 times a -5, which is going to be, that's going to be a plus 25. So this ends up producing 75. So when -5 goes in, 75 comes out. And there's, that's a thing. This one, probably a nice thing to do is to just show, look, this is the definition of this function. This function takes 2/3 of the input, it adds 12 to it, 2/3 of the input, and then adds 12 to that. I'm trying to make the output of this function become the number 32. So what I'm going to do is I'm going to say, look, this is the definition of the function, 2/3 of the input plus 12, and I want this to become 32, right? I want 32 to come out of this. So when I write this, I'm like, all I have to do is solve for x. So if I take away 12 from both sides, this is going to give me that 2/3 of x is the number 20. 20, yeah, 32 minus 12 is 20. And then I could do one of two things, right? I could multiply by the reciprocal here, so I can multiply both sides by 3/2 times 3/2. When I multiply the left-hand side by 3/2, this becomes 6/6, which is just a 1. So this is now just a giant 1, and I'm left with x. On the other side, I end up with the number 20 times 3 is 60/2. And if remember, the number 20 has a denominator of 1, so it's 20 times 3, which is 60 over 2, and 60 over 2 is 30. So the input is 30. So I could just test this. If I put the number 30 right there, right, half of 60 in there, it will give me an answer of 32. Right, last question on this page, number 6. Number 6 says, find the equation of a line through this point, 820, that makes a 90-degree angle. It is perpendicular to this line, 2x plus 3y equals -4x plus 12. Well, the problem with that line is it's not in slope-intercept form, it's not in standard form, it's not in point-slope form. So it's difficult for me to look at it and know what the slope of that line is. Because I'm asked to write a line that's perpendicular to it, I'm thinking I need to know the slope of this line so that I can do the opposite reciprocal to get the slope appropriate for a line that's right, or making a right angle with it. So I'm just going to take away 2x from both sides. This is going to give me that 3 times y equals negative 6 times x plus 12. Again, I just subtracted 2x from each side. Next thing I'm going to go ahead and do is divide everything by 3, all the terms. There's this term there's one term on the left, 2 terms on the right. They're all going to be divided by 3. Just pushing that factor or pushing a factor of 1/3 or dividing everything by 3. This is going to become y is equal to negative 6 divided by 3 is negative 2x, and then plus 12 divided by 3 is the number 4. So the slope of this line is negative 2. And because I want a line that's perpendicular to it, I have to have the opposite sign, right? So instead of negative, it has to be positive. And instead of being, like this is negative 2 over 1, instead of being negative 2 over 1, I need the reciprocal, which is up 1 over 2. So I'm going to be using this slope, positive 1/2, and it has to pass through this point, right? So the trick that I use is, look, if it has to pass through that point, I know that I could use this technique, y equals mx plus b. I know an x value, I know a y value, and I know my slope m is 1/2. I could plug those all into it and get what? Y is 20 equals 1/2 times 8 and then plus b. 20 equals, that's 4 plus b. So that means 16 is my y-intercept. 16 is, so the equation there is y is equal to 1/2 x plus 16. I'll write it right here. Y is 1/2 times x plus 16. So this line has 2 properties. First property is that it makes a right angle. It will make a 90-degree angle with this line. So if they're both drawn, they would be perpendicular to each other. And the other thing is that line will pass through this point, 820. Optionally, alternately, you could have plugged everything into the point slope formula. And I'll just remind you, it's y minus the y value that you know. So y minus 20 equals my slope, which is 1/2 times the quantity of x minus the x value that I know. That is the same equation. You can't see it right away, but if you were to take, for example, and add 20 to both sides and distribute the 1/2, you would get 1/2 x, and then 1/2 times negative 4 would be 1/2 times negative 8 would be minus 4, and then plus 20. So you can see the number 16 right there. This has some advantages. I like it. The other way is just fine too. All right, our last question is a bit wordy. And to be honest, reading this and interpreting what's going on is really what this question's about. Like, are you able to contextualize the things that we've done with finding least square regression lines? So researchers at BYU matched clients' ratings on a 45-item self-reported mental health questionnaire at the start of each counseling session with data on sunrise, sunset, rainfall, wind, pollution, and other weather variables collected by the university's physics department and the National Weather Service. That's coffee. They found that the more hours of sun there was in each day, the less psychological distress a person had. A distress index was created that ranged from 0 to 100. 0 indicated low stress and 100 was high stress. Okay. So this is like the calculated distress. So if I'm just, as I read this, I'm looking at the diagram, I can see that on my y-axis, I have this calculated stress index that's ranging from 0 to 100. And on my x-axis, I can see that I've got hours of sunlight, and it's anywhere from 0 to 16. And it can happen if winter in Alaska. The relationship between the hours of sunlight each day, x, and the psychological distress index, y, is approximated by the least squares regression line, y equals negative 3x plus 57, or 59 rather. And you can see that line's plotted. You can see it's got roughly a y-intercept there at 59, just below 60, and it's down 3 over 1. First question, A. Find the residual for the data point labeled A. So this point is right here. It's at A, and I can see that it has an x value and it has a y value, right? That x value and y value are from an actual person, right? They represent a person. And a residual is the difference between what the model predicts and this individual. And right here, I'll put a red dot. This red dot represents the y value that's predicted for this x value of 2. So if we think about it, we've got two things going on here. In this number 40 is an actual y value, right? And there's some y up here, right? There's some y up here that is a predicted y value. It's what the model predicts will happen. And we can see that this person has less stress than the model would have predicted, right? They're below that. So they're less stressed out than the model says perhaps they should be. So if we want to find this residual, right? A residual is equal to the difference between my actual y value, I'll notate that as AY, which is the actual y, the y from our data set, minus the predicted y value. That's the y that we get from the model. Well, this model, again, I'll remind us, is the equation y is equal to, what is it, 3, it's right on the page, negative 3x plus 59. So this model is y equals negative 3x plus the number 59. And I want to know what this model predicts when x is the number 2. So when x is 2, right, we're feeding this number into it. And when x is 2, what do we have here? Well, this becomes negative 6 plus 59, which equals 53. Yeah? So what does that get us? Well, that is our predicted y value. And the residual for this data point, right? And by the way, if I was to draw the residual is like this exactly. That's that line segment that's red right there. That's what we're talking about. It's like how much is this off by, right? Well, what is it? It's the actual y, which is the number 40, minus the predicted y, which was 53. And 40 minus 53 is the number negative 13. So the answer to this is my residual is negative 13. The person is less stressed than the model predicted. It's below that. It's below what the model says might happen. And you can see that every single one of these data points has its own residual. Some of the points, like this one right here in green, that looks like it's got a residual of nothing. Some of them have positive residuals. You can see these are above the line. And some of them have, like the one we just did, have a negative residuals. So that's just a little review of the residuals. Next, part B. It says, down here, Boise, Idaho has peak hours of sunlight of 15.2 hours in June. Okay, so in the month of June, lots of sunlight. Sunlight's great. Sunlight's beautiful. You know, we're getting into we just did daylight saving. We left standard time. I don't know. We've got less. It feels like we've got less sunlight now. Predict the calculated distress index for someone living in Idaho during the summer. So the prediction, right? What is that? Well, again, my model is y is equal to negative 3 times hours of sunlight, right? That's what x was, hours of sunlight. I'm just going to plug that in. It was 15.2, and then plus the number 59. So negative 15.2, or negative 3 times 15.2 looks like it's negative 45.6 plus 59. And when I combine those, I get y is 13.4. So pretty low considering the stress index ranges from 0 to 100. Feeling pretty chill in Idaho, lots of sunlight during the summer. And then finally, C, Nome, Alaska has about 4 hours of sunlight during the month of December. Use artificial light, right? Get a light bulb, UV, I don't know. Predict the calculated distress index for someone living in Nome, Alaska during the month of December. So same exact thing, right? Y, calculated distress index, is equal to -3 times 4 plus 59. So this is -12 plus 59. When I combine those, I get that Y is about 47. So definitely more stress than Idaho in summer, Nome, Alaska in December. All right, that's it. That's the end of the test. More stressed with less sunlight. Enjoy the sunlight when you can. On the weekend, get out, take a walk in a park. If you got a dog, take your dog for a walk. Play frisbee with your friends. Do something in the sun. All right, this is Mr. Roberts. Have a good evening, good afternoon. I will talk to you again later.